So we're continuing our discussion of fault tolerance and atomicity. And in sort of this, teaching these lectures makes me feel, in the beginning, makes me feel like those TV shows where they always, before a news episode, they tell you everything that happened so far in the season. So we'll do the same thing. So the story so far here is that in order to deal with failures, we came up with this idea of making modules have this property of atomicity, which actually has two aspects to it, one of which is an all or nothing aspect, which we call recoverability. The other is a way to coordinate multiple concurrent activities, so you get this illusion that they're all separate from each other, and we call that isolation. And the basic rule here for achieving recoverability was we repeatedly applied this one rule that we call the golden rule of recoverability, which is to never modify the only copy. And we used that rule to build up this idea of a recoverable sector, and we used that idea of a recoverable sector to come up with two schemes for achieving recoverability, one using version histories where you had a special case of this never modify the only copy rule, which was never modify anything. So for any given variable, you just create lots and lots of versions, never updating anything in place. And then we decided that that's inefficient, so we came up with a different way of achieving recoverability using logging. Then for isolation, we did this last time where we talked about serializability. Where the goal was to allow the steps of the different actions to run in such a way that the result is as if they ran in some serial order. And we talked about a way of achieving that with self-storage. In particular, we talked about using locks as an abstraction, as a programming primitive to achieve isolation. And in particular, the key idea that we saw here was that serializability implied that there were no cycles in this data structure called the action graph. And as long as you could argue that any method of locking, for a given method of locking, as long as you could argue that the resulting action graph had no cycles, you were guaranteed serializability, and therefore the scheme provided isolation. And in particular, a scheme we looked at near the end was two-phase locking, where the idea is that you never acquire a lock for any item if you've done a release of any other lock in the atomic action so far. And that's the reason why this is called two-phase locking, because if you look at the two phases being a lock acquisition phase, where the only thing that's happening is the locks are being acquired, nothing is being released, so the number of locks is strictly increasing with time. And then there's a certain point of the action after which you can only release locks, and you can't acquire a lock the moment you've released any given lock. And the way we argued this protocol achieved isolation was to consider the action graph resulting from some execution of two-phase locking, and argued that if you wanted that action graph to not have a cycle, then argued that if there was a cycle in that resulting action graph, then two-phase locking gets violated, and therefore two-phase locking provides an action graph which does not have cycles and therefore achieves serializability. So two-phase locking is fine, and it's a really good idea if you're into using locks. It has the property that you don't actually need to know. The action doesn't need to know at the beginning which data items it's going to access, which means that all you need to do is to make sure that you don't release anything until everything has been acquired, but you don't have to know which ones to acquire before the start of the action. You just have to keep acquiring or sort of on demand until typically you get to the commit point. And once you commit, you can release the locks. Now, in theory, you can release a lock at any given time once you're sure that you're not going to acquire any more locks. But that theoretical approach only works if you're guaranteed that there will be no aborts happening. Now, in general, you can't know beforehand when an action might abort. I mean, the system might decide to abort an action for a variety of reasons, and we'll see some reasons today. So in practice, what ends up happening is that when you abort, you have to go back and look through the log and undo the actions, run the undo steps associated with steps that happened in the action, which means that because the undo goes ahead and into cell storage and uninstalls whatever changes were made, it better be the case that when abort starts undoing things, it better be the case that the cell storage items that are being undone have locks owned by this action that's doing the undo. So what this means is if you have a set of statements here that are doing reads of X and a write of Y and things like that, it better be, and then you get, you have commit here. But this is the last point in time at which you're reading and writing, and after that you're doing some computation here, not involving any reads or writes. If you need, the action might abort anywhere here, because the process might, this thread might be terminated and the action would have to abort. What that means is that a release for a data item that's required by abort in order to undo the state changes that have been made, that lock had better not been released before here. Because if the lock got released here, then some other action could have acquired the lock and gone ahead and started working with the changes made by this action. And now, it's too late to abort. Someone else has already seen the changes that have been made. In fact, you can't be guaranteed now that later on you actually can regain the lock and the results would be wrong. So in fact, the two-phase locking rule really is that you can't release any lock until all of the locks have been acquired. And moreover, any locks that are needed in order for abort to successfully run had better not been released until you're sure that the action won't abort anymore. And the only time you can be sure that the action won't abort anymore is once commit has been done. So what that really means is that the release for all of the items the release of the locks of all of the items that are required for undoing this action had better happen after the commit point. And moreover, no items locks should be released until all of the acquires have been done. Now, the reason I've said this in two parts is that, if you're just reading a data item, you actually don't need to hold on to the lock of that item in order to do the undo, because all you did was read X. There's no change that happened to the variable X, which means although you need to acquire the lock of X in order to read it because you don't want to have other people making changes to it while you're reading it, you don't actually need to hold on to the lock of X in order to do the undo, because you're not actually writing X during the undo step. So that's the amendment to the two-phase locking rule, that things that you need in order to do undos for should only be released after you're sure that no aborts will be done, which means after the commit point. Okay, so this way of doing two-phase locking is actually a pretty good scheme. And it turns out that in many ways it's the most efficient and most general method. What that means is that there might be special cases where other protocols for doing locks of objects perform better under certain special cases compared to two-phase locking. But if you've bought into using locks in order to do concurrency control, and you don't know very much about the nature of the actions involved, then two-phase locking is quite efficient. I mean, there are variants of two-phase locking, but by and large, this idea is, it's very hard to do much better than this in a very general sense if you're using locking for doing concurrency control. But there is a set of problems. It's not like two-phase locking, as we've described it so far, completely solves the problem of ensuring that actions, perform well. And a particular problem that happens anytime you use locks, like here, is deadlocks. And we've actually seen deadlocks before, in an earlier chapter when we talked about synchronization of threads. And it's exactly the same problem. And the way you deal with it pretty much, is almost the same. So what is the problem here? Well, what could happen is that one action does read X and write Y, and the other action does read Y and write X. And now you intersperse the acquires and releases, so you do an acquire of LX here, and maybe you do an acquire of LY here, and here you do an acquire of LY, and you do an acquire of LX. And what could happen is that once you get to this stage where this action has come this far and is about to run this, and this other action has come up to here, now you're stuck because this action has to wait until that's released, and this action has to wait until that's released, and neither can make progress. So there's a few different ways of dealing with it, and the simplest way, and the way that turns out to be one that's often used in practice, both because it's simple and because once you implement the technique, you don't have to do very much else, is to just set timers on actions. So it's just to time out, and if you notice that for a period of time an action hasn't made any progress, then have a timeout that is associated with the action, and if the system notices that, or the action itself notices that it hasn't made any progress, perhaps in another thread, then just go ahead and abort this thread. Now it's perfectly okay to abort, and in this particular case, aborting either of these actions is enough, and the other will make progress, and then you're done. And then the action that got aborted can retry. So that's the first solution, is to just use a timer. And there's a school of thought that believes that in practice, deadlocks should not be very common. And the reason is that deadlocks occur if there's, there has to be contention for resources, and there has to be, contention from multiple threads for the same resources, and it has to be more than one resource. Because if you just have one resource, you can't really get a deadlock. Which means that you're sort of running multiple actions that are contending for a number of different shared objects. And what that suggests is if there's a high degree of concurrency like that and shared contention, then it may be hard for you to get high performance. So a lot of people think that the right way to be designing applications is to try hard to ensure that the degree of sharing between objects is actually quite small. So for example, rather than set up a lock on an entire big database table, you might set up locks at finer granularities. And if you set up locks at finer granularities, the chances of multiple actions wanting to gain access to the same exact fine-grained entry in a table might be small. And in that situation, given that the chances of a deadlock occurring are rare, timing out every once in a while and aborting an action is not going to be catastrophic. It's okay. It's a rare event. So rather than spend a whole lot of complexity dealing with that rare event, just go ahead and let something abort. Let an action that hasn't made any progress abort. Moreover, these timers are necessary anyway, because an action might end up getting stuck in an infinite loop, or it might end up getting stuck in a situation where it's not really waiting for a lock, it's just there's a bug in it. There's a problem with it. It isn't really making any progress, and maybe it's consuming resources and no one else can make progress. So the system anyway needs a way to abort those actions, and it needs a timeout mechanism anyway. So why not just use that same mechanism to deal with deadlocks as well? Some other people, probably somewhat in a minority, but some other people believe that deadlocks might happen, and when they do happen, perhaps because the granularity of locking in your system is not fine-grained, then you don't want to get stuck. And you want to optimize, at least you want to do reasonably well rather than waiting for some long timeout period before aborting an action. And people who believe that build a data structure called the waits for graph. And the best way to understand this is, imagine you have a database system which supports, isolation, and anytime you want to acquire a lock, you send a message to this entity in the database system called lock manager asking to acquire a lock, and anytime you release it, you do the same thing. So what that lock manager can do is to keep track for each lock, it can keep track of which actions running concurrently has acquired that lock and which action is waiting for a lock. And what you can do now is to build up a graph of actions and locks and look to see whether there's some kind of a cycle where you have action A waiting for lock B, and lock B is being held by action C, and action C is waiting for lock D, and lock D is being held by action A. So when you have a cycle in this graph, then you know that you have a deadlock and none of those actions can make progress. So go ahead and kill one. And you can be sophisticated about deciding which one to kill. You might kill the one, for example, that's been waiting the shortest amount of time because the others have been waiting longer, so they might make progress, or you might have other policies for deciding which ones to kill. So in practice, both these systems are used sometimes by the same system, combining these ideas. So for example, if you look at like an Oracle database system, it uses primarily timers. It doesn't see, at least from what I could tell, it doesn't seem to have any mechanisms for really doing this check of a waits for graph. It just uses timers. And one of the oldest transaction processing systems was a system called CICS from IBM, which also basically used timers. But there are other systems like, for instance, IBM has a system called DB2, and Microsoft SQL Server that both use this waits for data structure. And in fact, Microsoft's system seems to have 100,000 different knobs for deciding how to turn off deadlocks, including your ability to set various priorities on different actions that might be running. And it's not actually apparent that those knobs actually are useful for anything or how you set them, but they have a lot of things that you could set. Sounds familiar? Now, you can combine these two, and I think certain products combine these two ideas. So rather than, one decision you have to make is to decide when to check this waits for graph. And an aggressive way of doing it is the moment anybody does an acquire or anybody does a release, you look in particular an acquire, you update your lock manager's data structure and immediately look to see if you have a cycle. Of course, that takes time and effort. So you might decide not to bother, but rather periodically look for cycles in this waits for graph when a timer fires. So every 3 seconds, go ahead and look for cycles. So you might combine these ideas in a bunch of different ways. Now, if you recall from several lectures ago, another way of dealing with deadlock is to order all of the locks that an action might be able to acquire in a particular order and ensure that all of the actions acquire the locks in exactly the same order. And that will ensure there are no cycles because you have to go in the same order. But that idea requires you to know beforehand which data items you wish to gain access to, and that's often not possible in many systems in which you care about isolation. So that's usually not adopted in any, at least in any database system. Okay. So we talked about deadlocks. We talked about when you can release a lock that you require in order to abort. As you can't release it typically until, in reality, until the commit point is done. The last issue we need to talk about is an interaction between logs and locks. And this interaction has to do, so we already saw what happens when you abort. When you abort, you need to undo, so you better make sure that to do the undo, you have the locks for those cell items. But suppose you don't have to abort, but suppose you crash. Suppose the system crashes and recovers. At that point, when it recovers, it's going to run a recovery procedure which has some combination of redoing the winners and undoing the losers. Now, when it's undoing things and redoing things, it needs access to items in the cell store. And we've already seen that when the system is normally running, in order to change items in your cell store, you need to gain access to locks. So the question now is, during crash recovery, when the system is running this redo-undo thing, where do you get these locks from? And do you need to gain access to the locks? Now, in general, the answer to the question might be that you need to be very careful and perhaps need access to the locks when you're running recovery. But there's one simplification that systems typically make that eliminates that requirement. And that simplification is that during crash recovery, don't really allow new actions to run on your system. So when a system crashes and it's recovering, don't allow new actions to run until recovery is complete. And only then do you start new actions. So what this means is now we just have to worry about ensuring isolation purely during recovery without having new actions coming in and muddling things up. So the question really to think about is whether before the crash, in the log, because the log is the only thing you have in order to do recovery, whether in the log you actually need to keep track of which locks were being held when the system was running just fine. And if it turns out that the log has to encode in it the locks that were being held, it could be quite complicated and a little bit messy. But if you think about it, the nice thing is that we don't actually have to encode the locks at all, to store the locks at all. The locks can be completely in volatile storage. And that's because when you start off and you have a log which has various redo items and undo items, in any element of the log, let's say an item X has been updated in that log entry, then you know for sure that at the time this log was written, this log entry was written, the action that was making this update did hold on to this lock. And that this change being made here that got written into the log was in fact isolated, assuming the locking protocol was correct, was in fact isolated from everything else concurrently that was going on. And so although it's not explicit, the log actually encodes in it although the locks are not explicit, the log encodes in it the actual serial order, some serial order of execution that did provide isolation before the crash. And therefore, if you just blindly go back through the log and make those changes in sequential order, then you're assured that the changes you make are in fact going to be isolated from one another. So you don't actually have to worry about storing the locks before the crash into the log. And that makes life quite simple. Okay, so that wraps up the discussion of atomicity, and in particular, isolation. So for the rest of today and next time, we're going to be talking about some uses of atomicity. And the plan is the following. The plan is the first application of atomicity, which actually is the umbrella for a number of things we're going to be looking at, is a transaction. And a transaction is defined as an atomic action that has a few other properties that it holds. And the first property is consistency. And the second property is durability. And the second thing we're going to look at next lecture actually is atomicity when you have a distributed system. So it's using this using atomicity on one computer to build out a system that provides atomicity in a distributed system. So we'll talk about consistency the rest of today, and the recitation for tomorrow looks at a paper for reconciling replicas, which is a particular aspect of consistency. And then the next lecture next week, we'll talk about multi-site atomicity, and the recitation next week, we'll talk about durability. And once we do all of that, that kind of wraps up this fault tolerance part of 6033. So let me first talk a little bit about transactions. So transaction is an atomic action that has two other properties associated with it, and people in the literature often, or in colloquial terms, often refer to transactions as having a property called the acid property. The acid stands for atomicity, consistency, isolation, and durability. And you'll see this term a great deal in the literature, and people will use this all the time. And for various reasons, the way we've done things in this class, some of these terms are used in slightly different ways from the acid term. So when most people, at least in distributed systems and database systems, use the word atomicity, what they mean is what we meant by recoverability. So it's all or nothing. When they use the word I here for isolation, they mean exactly the same thing that we did. And consistency and durability are fortunately going to mean the exact same thing. But really the point to notice is that these two properties, atomicity and isolation, are things that are independent of an application. They just are properties of atomic actions. That an atomic action just can be recoverable and can be isolated. And you don't have to worry about what the application is. It could be an application in database systems. It could be something in a processor where you're trying to provide recoverability or isolation for instructions. These are properties that are, in some sense, somewhat more fundamental and lower layer properties than these other two properties. So consistency, what consistency means is the property of an atomic action that is some application-specific invariant. So consistency just says that if you have a consistency of a transaction says that if you have a transaction that commits, then some set of consistency invariants must hold. And I'll describe some examples of what this means. So consistency just says that there's some application-specific invariants that must hold. And durability says that if a transaction commits, then the state changes that it's made, that the data items that it has changed, have to last for some period of time. And the period of time that they have to last for is defined by the application. And there are many examples. So a simple example of durability might be that the changes made by an atomic action just have to last until the entire thread finishes. And at the other extreme, you could get into semantics of durability, which say that the changes made by an atomic action have to last for 3 years, or for 5 years, or for forever, which is a really hard thing to solve. But you might define semantics that have to do with, this relates to the permanence of data. For how long do you want the changes that you made to last and be visible to other atomic actions? So there are two cases for consistency that we need to talk about. The first one is consistency in a centralized system. So an example of this, and the most common example of this is in database systems that support transactions, where you might have rules that are also called integrity rules, for deciding whether you're allowing a transaction to commit or not. So let me give you a couple of examples of this. So let's say that you have a type of database system is a relational database system where all of the data is stored in tables. So for example, you might have a table storing the student ID, the student name, and let's say the department that the student belongs to, okay? And let's say the departments have IDs, okay? And you might have another table in your system that stores a department ID and a department name. Now you might have a transaction that makes updates to entries in this table, one or more rows in this table, or it could actually make updates to just specific cells of this table. So it could add a new student ID, add a name, and add some department ID. Now, the kind of constraint we're worried about, the kind of invariance we're worried about are things where the person who's designed this database might say that you're not allowed to add a department ID that's non-existent. And what that means is that there are these two tables, and you shouldn't allow any transaction to write a department ID which isn't already in this table. So if 43 might be in this table, and 25 might be in this table, but a number that's not in this table shouldn't be added here. And so the transaction processing system will in fact not allow this transaction to commit if it's writing a value that isn't in this other table. And for those familiar with databases, the way relational databases, there are these two tables called this T1 and T2. This might be a primary key. Department ID might be a primary key of T2, defined as what's called a foreign key in T1, which means that you're not actually allowed to add something to a foreign key if it isn't already in the other table where that same column is a primary key. So there are rules like this in most relational database systems, and there's a variety of rules like this that all have to do with maintaining the integrity of the data that you add here. Now, this has nothing to do with isolation. It has to do with atomicity, because these rules are defined at these rules are typically checked at the commit point. Because until then, anything could happen. So right before you commit, there are these invariants on the data that are application specific that you need to check. But it has nothing to do with locks. It has nothing to do with anything. It sort of presumes atomicity, and after that, it checks these application specific rules. Now, you could get quite sophisticated. Some of these things about primary keys and secondary keys are things that are checked by most transaction processing systems. But you could get quite sophisticated about these rules. For example, you could have rules that, let's say you have a database storing employees and their salaries. You could have rules that say that anytime, an employee gets a raise, then everybody else in the same, peer group also gets some kind of a raise. And so, you wouldn't allow any transaction to commit that didn't ensure that invariant to hold. And checking these things could be quite difficult, and most systems don't actually do a really good job of checking these things. The sets of rules they allow you to write is quite limited, because checking it is quite hard, because when you're trying to commit a transaction now, you might have to check a large number of rules, and some of them could be both time-consuming and complicated. But the main point here is that these rules are application-specific, and that's what defines consistency of the data that you have. The more interesting case for consistency, and the thing that's going to occupy us for the rest of today and tomorrow, is consistency in distributed systems. In particular, when the same data gets distributed, typically for fault tolerance and for availability, to ensure that the data is available at different locations, you end up with consistency problems. And we've already seen a few examples of this. One example of this is in the domain name system, which maintains mappings between domain names and IP addresses. And if you remember, in order to achieve availability and good performance, these mappings between DNS names and IP addresses were cached essentially on demand. Whenever a name server on the internet made an access to that name, it aggressively cached the mapping results. And so now you have to worry about whether the data that's cached somewhere out on the internet is in fact the correct data, where correct is defined as the data that's being maintained by the primary name server. And if you think about what DNS did, it actually used a mechanism of expiration times to keep this cache consistent. And what that means is that the only time you're guaranteed that the data in a cache is, in fact, the data that's stored at the primary name server for that name is when this expiration time finishes, and the first access after the expiration time requires the name server to go to the original primary name server and do a lookup of the name. So the rest of the time, you can't actually be guaranteed that the data is consistent. And in other words, you're not getting what's considered strong consistency. So what is strong consistency? So one way to define the semantics of what it means for data to be consistent in a distributed system is it's sort of a natural definition, which is to see that anytime you do a read, anywhere, any node does a read of some data, read returns the result of the last write. So that's one notion of consistency, and a system provides strong consistency if you can ensure that every read returns the result of the last write that was done on the data. And this is really hard to provide, because what it typically means is that the data is widely replicated or cached. Then anytime anybody changes the data, you have to make sure that all of the copies get that change. And even if you work really hard to invalidate all of the entries and make changes to it, there are these small windows of vulnerability where, in fact, in DNS, for example, even the first access that you make to the server after the expiration time may not guarantee that when the response returns, the response is in fact the newest response, because the primary name server could send a response, and while it's coming back to the person who made the query, the data could get changed at the primary name server. So it's really hard to guarantee this at all points in time in a distributed system. And it gets much harder when there are failures, making certain copies unavailable, or making access to a primary, in the DNS case, unavailable. So in practice, in most systems, the kind of consistency that people try to get is eventual consistency. Or they try to approximate strong consistency in some other way. And eventual consistency just, it's a little bit of a loser notion, but what it says is that there might be periods of time where things are consistent, or that the system is doing work in the background to make sure that all of the copies of a given data item are in fact the same and are the result of the last write to that data. Again, the notion of eventual consistency depends a lot on the application. So really to specify this precisely, you have to look at it in the context of the application. In different applications, you'd have different notions of consistency and eventual consistency. So we looked at DNS as an example. Another example to look at is something you might be familiar with, which is web caches. So web caches, the way web caches work is that, for example, your browser has a cache in it, and there might be web caches located elsewhere in the network that capture your requests, and people use web caches to save latency or to prevent slamming a web server that might otherwise get overloaded. The semantics here are usually that you don't just return stale data. If the data has changed on the web server, it might be that you actually want to return good data to the client. So the way this is normally done is for the client, or for cache, for any cache, to first check with the web server to see if the data has been changed since the last cached version. So let's say that the client the cache went to the web server at 9 in the morning and had to go there because it didn't have the data in the cache, and it got some data back. The data has a timestamp on it. Then the next time somebody makes a request to the cache doesn't just return the data immediately. What the cache usually does is to go to the web server and ask the web server if the data has changed since 9 in the morning. If the data has changed since 9 in the morning, you might retrieve the data. You would retrieve the data from the server. If not, then go ahead and return the data to the client. So this is also called if modified since. Because what you're saying is the cache is telling the server, send me the data if it has been modified since the last time I know the version of the data that I have. And a convenient way to represent that is as a timestamp. It's just a version of the data. So you can see that this actually provides a somewhat stronger consistency semantics than DNS, because in DNS the data could have changed and your cache just has outdated data. But for the application that DNS is used for, it's perfectly okay for that to be the case. Now, in general, in distributed systems, there's a trade-off between the consistency of data at the different replicas and availability. So availability just means that clients wanting data should get some copy of the data. Now, if the system is strongly consistent, then the copy of data that you get is in fact the result of the last write. But the trade-off occurs between availability and consistency because in many distributed systems, your networks are not reliable, or nodes themselves are not reliable and they might fail. So in the presence of failures, say network partitions or failures of nodes, it turns out to be really hard to guarantee both high availability and strong consistency. As a sort of a trivial existence example of this, if you have 3 copies of the data and you weren't very careful about figuring out about your write protocol. So let's say that your write protocol was to sort of write to one version, and then your read protocol was to just read from some other version, and for some process in the background to transfer the replica from the first version that the client wrote to all of the other copies, then there would be periods of time, if the network were partitioned, you could end up in a situation where the version that you're reading, that a given client is reading, is not actually the last version of the data that was written. In fact, if you've started thinking about DP2, Design Project 2, really, one part of it gets at how you manage replicated data. So for example, when the archiving, the utility that does the archiving publishes data, one approach it might take is to publish the data, the data that it wants to archive, to all of the copies, to all of the replica machines. And the read protocol might be to read from one of them. Now, if you ensure that the write protocol finishes and succeeds only when all of the all of the replica machines are updated, then you can try to get at a decent version of consistency. But you need to be able to do that when failures occur. The network might fail or nodes might fail, and you need to do that. You need to figure out how to do that. But you might decide that writing to n copies and reading from one copy is difficult or has high overhead. So you might think about ways of writing to certain subsets, writing to a subset of the machines and reading from a subset of the machines to try to see whether you could come up with ways to get a consistent version of the data. Or you might decide that the right way to solve the problem is not to try to achieve really strong consistency in all situations, but to relax the kind of consistency you want and maybe a different version of semantics. As long as you're precise about the semantics that your system provides, it might be a different solution, a reasonable solution to the problem. So one interesting way in which people achieve reasonably strong consistency in tightly coupled distributed systems, and distributed systems that aren't across the internet where a network could arbitrarily fail, but in more tightly coupled systems is in a multiprocessor. So if you have a computer which has many processors, so let's do it. And the shared memory, I mean, the abstraction here for this multiprocessor is that of shared memory. So you actually have memory sitting outside here, and these processors are reading and writing data to this memory. The latency to get to memory and back is high, so as you know, processors have caches on them. So as long as the memory locations that are being written and read are not shared between them, these caches could function just fine. And when there's an instruction running on one of these processors that wants to access some memory location, you could just read and write from the cache. So things would just work out. The problem arises when there's a memory location being read here that actually was previously written by this processor. And if you read it here, then you might get an old version of the data. And if you just think of just memory as the basic abstraction, virtual memory, then this is bad semantics because your programs wouldn't function the same way as they did when you just had one processor or when you didn't have the caches at all and you just went directly to memory from multiple processors. So the question is, how do you know whether the data in a cache is good or bad? Now, checking, like in the web caching case, checking on every access whether the data has changed is not going to be useful here because the amount of work it takes to check something is about the same as the amount of work it takes to read or write something, because that already takes you've taken the latency hit for that. So that approach isn't going to work. So the solution that's followed in many systems is to use two ideas. The first idea is that of a write-through cache. What a write-through cache says is if there's a write that happens here, or a store instruction, the cache gets updated, but in addition to the cache getting updated, the data also gets written through on the bus to the memory location here. The second idea, so that's the first idea, is to use a write-through cache. The second idea is, because this is a bus, all of these nodes can actually snoop on this bus and see what activity there is on the bus, because it's a shared bus. It's a very special kind of network, as I said. You can't apply this idea in general. This is a very special kind of network where, because it's a bus and nothing fails, or the assumption is nothing fails, everybody can check to see what's going on the bus. And anytime there's any activity on the bus that corresponds to something that's stored in any node's cache, you can do two things. You can actually invalidate that cache entry, but you can actually also see what the update is and go ahead and look at the change that was being done and update your cache. And this idea is called, sometimes called a Snoopy cache, because you have these caches that are snooping on activity that's occurring in your system. And this is one way in which you can achieve something that resembles strong consistency. But it actually turns out, if you think hard about it, a precise version of strong consistency is really hard to achieve. In fact, it's very, very hard to even define what it means for any read to see the result of the last write. Because when you have multiple people reading and writing things, when you get down to the instruction level, it turns out to be really hard to even define the right semantics. A lot of people have worked and are working on this kind of thing. But this is a little bit of a special case, because this kind of solution applies only in a very tightly coupled system where you don't really have failures and everybody can listen to everything else. But it's interesting to note that there are cases when you can achieve it, and that's why this is interesting. It's practically useful. So the main thing about Design Project 2 that relates to the consistency discussion is for you to try to, or at least one part of it, in case it wasn't clear from the description of the project, is for you to think about what kind of consistency you want and come up with ways to manage these different replicas. So we're going to stop here. Next week, we'll talk about multi-site atomicity. Tomorrow's recitation is on a system called Unison, which also looks at consistency when you have mobile computers that are trying to synchronize data with servers.